So, historically, the chemists would like to use ionization energy or binding energy as the reference. The physicists like to use kinetic energy. So you will see a different preference. And historically, what people do, in fact, what is shown here, because this is done by a gas phase spectrometer. This spectrum is taken by a gas phase spectrometer. You're talking about solid state chemists or physicists. They would plot this in exactly reverse. In other words, they would start the kinetic energy from zero from this side, okay, and the binding energy from zero on this side and go high in this way. So that's the convention that people use. So I just want to point it out because historically, the physicists like to think in terms of kinetic energy. So they always start from zero. They don't care so much about the ionization energy. And then when the chemists come along, they just kept the convention. They keep the binding energy this way and leave the kinetic energy going this way, the full electron going this way, from zero to high, zero to high like that. This is plotted in a reverse manner against convention. Okay, so I just want to point that out when you see XPS spectra or full electron spectra that later on. Now you may say that, well, okay, so that's fine. Okay, so that corresponds to so-called Koopman theorem. So Koopman said that, well, I can approximate my understanding, right, using my orbital energy, right? So these are MO diagrams. So Koopman basically say that this binding energy here corresponds to my molecular orbital energy, right? In this picture, ejecting a single electron from that orbital one at a time. That's the Koopman's view. However, Koopman is of course not right because you cannot think in terms of MO diagram because you really have to think the entire wave function. So an improved picture is this picture, is that you should think about the entire electronic state. So you should think of neutral ground state as drawn in this electronic configuration. You could think of the ground excited ionic state, treating the entire package of electron as a whole, as the wave functions, right? So this is a big wave function. This is a little phi, if you like, and so forth. So you have the ground ionic state called the X state, and then you have the first excited state A, B, and C. So this generic notation is always the same. So you should treat them like proper wave function, and then you will see more interesting thing happening. Okay, if you do that, what happens? Well, you treat it like a state. If you treat it the molecular electronic configuration like this, you can then plot your total wave function like this, right? You can plot it as a function of distance, right? Remember your Morse potential, right, for diatomic orbitals. Some of you may remember. This is intermolecular distance, right, between one atom, stationary atom, and the other atom as you put them together, as we move them together. So you can think of one atom here, right, one atom here. You're moving another atom along some axis to form a stable molecule, right? So in diatomic spectroscopy, it works, right? So this is how you call this potential energy curve, right? So as the atom get closer and closer, you form a stable bond. Sorry, the atom is actually here. This is the other atom. This is the equilibrium geometry. When this atom moves to here, you have a potential well, and this atom gets trapped in here and is stationary, right? So this is diatomic molecular picture, and you can do the same for triatomic like water and so forth. And then instead of one axis, you have an entire map because you have along one axis in one direction, you have another in another direction. You get similar type of picture like this. So this is potential energy curve for ground neutral ionic state for AB. I'm just drawing AB atoms. And you can say, well, I can take the whole thing, and instead of treating it like a little one electron at a time, like an animal diagram, I treat the entire thing, and then I can say that, well, I can say that the ion state, I just remove one electron, appropriate it from one of the orbital, and then we calculate. What you got is a system with one less electron, and that is the ion. And the ion would also have similar type of potential energy curve. Okay, so you generate all this little potential energy curve for system with one less electron. They are no different than system with complete set of electron as the neutral state. So this is neutral state, and these are ionic state, right? So when you're talking about transition, you're really talking about state-to-state transition. You absorb the entire photon, and so you're exciting from one state to another. Okay. So what you're talking about here is that, of course, in all this potential energy curve, on top of it, it has all the vibrational energy as well, right? Because you have little vibration along. So on top of this, there's vibrational state, like that. I hope some of you have seen spectroscopy. There's little vibration state, and this width here corresponds to the vibration of the atom along this potential energy curve. As you go up to higher vibration, they vibrate at a bigger length and so forth. And then when you go to really high, the atom could break because it then separate, right? This atom from here to here. So the spring, this is how we draw our picture, right? The spring here, right, can vibrate here to here. So this like this, right? So so this so-called potential energy curve, but drawn with all this vibrational energy level. So when you make the transition from the ground vibrational state, ground electronic state from here up, right, vertical transition corresponding to absorption of photon, like this, you will excite your system to each of these when it crosses. So you get all this line excited. And that's how you can see, right? That's why you can see these little peaks that you see. They correspond to the vibration of the ion itself, of the ion's potential energy curve, the ion that you see. Okay, so that's why we can for electron spectroscopy, even for gas phase, chemical physics is very powerful because you see all the excited state, all the vibrational state of the ions, right? How they vibrate with one less electron, and you will see the overlap of this, right? This one, for example, the second one, overlap more in this vertical transition. That's why you see more peak like this. Whereas this one only overlap a couple of them, and you see less, right? So it contains quite a bit of information about this state-to-state transition. Okay. So yes.
What about the relative intensity? What does that indicate?
Okay, so that's a good question. How do you obtain the relative intensity, right? When you make a transition from one to another, you can calculate this. So let me write down, right? So you have let's say phi naught is this big phi naught is your ground state, neutral state, right? And then you have phi plus, let's say, right? Is your let me just phi plus A for my first excited state, right? First excited state, and how do you get the intensity out? Well, in quantum mechanics, right? You're making a transition from the ground state to an excited state, right? Ground to excited state. So how do you write this? In quantum mechanics, you write the probability of making a transition from here to here, right? And the probability will be proportional to, you write it this way, you write a wave function, right? You have psi of naught, psi of A star, right? But like that, and some operator in the middle, all squared. Okay? If you if you like, I can rewrite this. If you don't know, this is Lewis Dirac notation. You can write it as an indigo, right? Think of it as an indigo like this.